for the next little while, okay, for the next several, okay, we're going to go pretty in depth into things, okay? Physical and chemical control, I think, is actually quite easy because it's just here they are. You've got to remember what does what and why it does what it does. But as we get to antibiotics, it's going to get more complicated, okay? So, and that's up next. So that's why it's critical that you fill in as much as you can from your slides before you come here. Because if you're trying to do terminology and concepts at the same time, it's not going to be very successful for you. Does that make sense? Okay. So the new slides should be up no later than Thursday night. So yeah, you should have over the weekend, make sure that you fill it in and start making notes. So when you come here, we can have discussions and you're not, this is what's happening as I've started to look at how some of the exam answers were done. Okay. Some of the questions that I thought everybody would get, they didn't. Why? Because it was on eukaryotes. How many weeks ago did we do eukaryotes? 3 or 4 weeks ago, okay? And a lot of people said, oh, that's okay. I know those. I don't have to worry about those. Oh, no, you had to know it. There were very simple questions like, which one is not an organelle? You know, that kind of thing, okay? That were missed by 60%, okay? That's not going to cut it here because here, now you've got new, and that's stuff that you got in your prereqs, right? So now you've got new things to do, new things that you haven't had in any other class, terminology plus concepts. If you're just coming to class and saying, well, you know, we're going to fill in the blanks, I'm going to go by pretty fast. This is pretty dense material. I'd rather talk about how you applied it, right? That's where you're going to get questions about, is how do you apply it? Will it kill endospores? Will it not? How long do you have to do it? What does it target in the cell? If I'm going over that and you're still stuck on terminology, are you going to get as much as you can out of the lecture? Not possible, okay? Because you're going to be on the details trying to write things down. So, okay, you might say, oh, well, you know, this really isn't hard in terms of what? What are the reasons that people don't do well in micro? Time and tools. So I'm giving you the tools to do really well here. Okay, it's up to you to put in the time and the effort. Okay, is that good? Cool. All right, so let's see how you did on this little thing. Okay, pretty straightforward. Let's see. What is the purpose of sterilization? You're killing everything, including endospores. So when you hear sterilization, yeah, it's killing endospores, everything. Okay, which of the following process is the process that inhibits the growth of microorganisms on living tissues? Living tissues changes the game. Can you ever sterilize living tissue? Never. Okay, the only way to sterilize skin is to burn it. We don't do that, okay? So what is the term that we use? It's what? Antisepsis. Good. Disinfection. Okay? When you disinfect something, what are you killing? Okay, have you got vegetative cells? Okay, what about non-vegetative cells? Not usually. What about endospores? No. Okay. So what does it work best on? Non-living surfaces, okay? You do not disinfect skin. If you say, oh, I'm going to disinfect the skin, I know you're not clear with your terminology, okay? Because what is the term you use when you're trying to clean microbes off skin? We just did it. What is it? Antisepsis, right. Get used to saying these terms. Get used to using them. Okay, bacteriostatic. What does bacteriostatic mean? Okay, are you killing them? No, you're halting their growth. Okay? Off the top of your head, if you read this chapter, What is an easy way to slow or to something that's bacteriostatic?
Cold temperature.
Refrigeration, cold temperatures. Good. Yeah, that is that. So all you do is you inhibit the growth, but you're not going to kill them. Okay? Now, in micro, why do we care about that? Because there are some microbes that are happy to grow in cold, like listeria. Okay? Just because you have refrigerated soft cheeses and meats and ice cream doesn't mean you're not going to get listeria. Okay? And that's a problem. I mean, we keep seeing listeria outbreaks all over the country. Okay? And who is most susceptible to a listeria infection? Pregnant ladies and immunocompromised. Okay? And the very old and the very young. Okay? But yeah, it's when you're pregnant, they tell you, don't eat soft cheese. Be careful about eating deli meats. Make sure things are refrigerated properly, okay? So, all right. What's the purpose of prophylaxis in micro? Prophylaxis, what is it for? Prevention. Yeah, prevention. Okay, chemotherapy involves using chemical agents that target and kill harmful microorganisms in the host. That's what chemotherapy. Remember, we talked about this before. Don't think about chemotherapy just in terms of cancer. Anytime you give a chemical to treat something, that's considered in micro chemotherapy. Yeah?
Okay, so chemotherapy is any form of chemical treatment, including the chemotherapy we think of with cancer, that often damages other cells as well.
Yes.
But in the book it talks about how that it's targeting only the microorganisms or the cells of that, like the mass. So why is it that the human cells are also affected by the chemotherapy?
It depends on what chemotherapy you're talking about. If you're talking about penicillin, our cells aren't going to be touched. The microbes will be touched. If you're talking about erythromycin or another ribosome inhibitor, our ribosomes might be affected. With chemotherapy, what are you trying to do? You're trying to kill human cells that have a dysregulated cell cycle. It's going to go everywhere, systemic. So, okay, so you have to look at the agent. What are you using? Okay, great question. Okay, number 7. Which of the following best describes a bactericidal? Cidal means what?
Kill.
Death, kill, okay? It kills bacteria. Antibiotics are naturally produced by microorganisms to kill or inhibit. Okay, what's our first antibiotic? Penicillin. Good. Okay. So what's true about bacteriostatic? They prevent reproduction. They don't kill. And which is the most effective method for sterilizing? Autoclaves. How many got 10 out of 10? 9? 8? 2? Okay. All right. Have you seen the autoclaves in lab? No. Ask your lab instructors if you can take a peek at the autoclaves, okay? All right, we're going to talk about autoclaving. I mean, it is critical for healthcare. Oh my gosh, you need the autoclaves. Okay. All right. Okay. So let's get going with this. Put mine out. Okay, so we've got physical and chemical control of microbial growth. All right, so let's go. So when we're using physical or chemical methods to destroy or reduce the number of microbes in a given area, okay? So we've gone through some of these terms, okay? Sterilization, disinfection, Antisepsis, when you think of antisepsis, what should you think of? Skin and body surfaces. Okay, sanitization. What does sanitization do? It just gets the microbe numbers down. Okay? All right, that's all sanitization does. Okay? All right. So, chemotherapy. We've talked about this one. This is you treat a disease with some kind of chemical substance that hopefully does not affect the host. Prophylaxis is prevention. Bactericidal, okay, is a substance that kills. Bacteriostatic, okay, inhibits the growth of bacteria, okay, but yeah, it doesn't kill them. And an antibiotic, we've talked about what antibiotics are. These are chemical substances usually produced by a microbe in small quantities that kill or inhibit another. Okay, asepsis. Okay, when you hear about aseptic technique or aseptic something, you use this in lab, right? Okay, what do? You try and get stop the spread of microbes into areas or to others, okay? We're going to talk today about pasteurization, and this is where you use heat to reduce the number of microbes and hopefully destroy some of the spores. It depends on the kind of pasteurization. We're going to talk about all different kinds, okay? Sanitary. This is soap and detergents, okay, usually soap and detergents, and they usually are with inanimate objects, okay. All right, so we've kind of gone over this already about the difference between sidal and static, okay, so I'm not going to spend a lot of time on that, but let's talk about temperature, okay. What happens when the temperature goes down? Okay, yep, so temperature goes down, so does the metabolic rate and diffusion rate. Okay, so cold can be used to slow things down, not necessarily kill everything though, okay? Tough to kill with that. Okay, so let's talk about environment. We look at environment when we talk about microbial control. We look at what the temperature is, we look at pH, we look at how much organic matter is there. And when we say organic matter, okay, what does that mean? When you say organic matter, what is that? Yeah, it's got carbon in it. Okay, so would barf be considered organic matter? Oh yeah, okay. Where in the environment are you going to find organic matter? Yeah. In the soil. Yeah, in the soil. Yeah, there's a lot of organic matter in the soil. So in the environment, think about where you might. Okay, I'm sure there's organic matter on those doorknobs. Leaving the classroom, I would guarantee it. I bet there's organic matter on your phone, right? Okay, so let's take a look at a couple of other things, okay? When you have extra carbon there, the organic matter will suck up the whatever the agent is that you're trying to control their microbes with. And so what do you have to do? You either have to increase concentration or you have to increase the amount that you're using, or sometimes both. Okay, so because the organic matter will just suck it up. Okay, presence of solvents and chemicals. Okay, we need to know how many microbes. This is important when you think about, okay, do I have 100,000 microbes or do I have 10 to the 11th microbes on this? Okay, what's the age and stage of the life cycle of the microbe? Is it actively growing, metabolically active, or not? Okay, we also have to look at cell structure and the walls. Okay, so if it's gram positive, we'll have one strategy. If it's gram negative, we'll have another strategy. If it's mycobacteria, What's unique about mycobacteria? They don't have what? They don't have any walls. Yeah. Cysts, endospores, all of that good stuff. And is it prokaryotic or eukaryotic? Okay? So all of these things have to be taken into control. So, or taking into consideration while we're trying to clean something. Okay? Do you remember this at the beginning of COVID when nobody knew what COVID was? Do you remember this back in 2025 years ago? And they would joke about how you have to wipe down your groceries and your mail with stuff, and people were spraying it with Lysol and all this stuff. Okay? Now that you've had micro, and especially this coming up, you would have heard, oh, it's an envelope virus? I'm good. Why? Because what gets envelope viruses? Those are the easiest to kill. Soap and water. Yep, that's all you needed. And you know what? Now that you've known about UV light, stick your stuff out in the sunshine. It'll kill the virus, right? But back then, you know, as soon as they said it was an envelope virus on March 20th or something, 25th, so I was like, oh, phew, good. That's good. But what happened to the rest of the world? They were all like, oh no, I've got to wash my chips. Okay? All right. So, all right. I put an outline here to kind of help you with trying to organize things and to help you with your one-page tests. I've talked to some folks after the exam. The one-page tests helped a lot. Okay? Just finding one topic and writing all that you remember about it. Because as you're finding out, micro is not just about definitions, it's also concepts, right? Concepts and applying them. So just put a little outline there that you can use. All right, here's the relative resistance of microbes. You can't really see that with this lamp. So let's turn this off here. Okay, most resistant, endospores, right? We kind of knew that because they're so, the whole reason that the bacteria make endospores is to survive harsh conditions. Okay, what's the least resistant? Viruses with lipid envelopes. Ta-da! Yeah. Why? Because as long as they've got that layer of lipid, that layer of fat, soap is going to disintegrate that membrane and the virus falls apart. Okay, gram-positive bacteria, viruses without envelopes, fungi, gram-negative bacteria, they're a bear to treat. Vegetative protozoans, cysts, mycobacteria, endospores. Okay, what diseases mycobacteria cause? Oh boy. Okay. Walking pneumonia. Yes, walking pneumonia. You've heard of mycoplasma pneumonia. There has been a lot of cases this winter that were mycoplasma pneumonia. Okay? Yeah. So it might be good as you go along through this, and you have some examples so you can remember. What are some of the gram-negatives we talked about? Okay, what does this do? This strengthens the link between your cards and all of that and what you're learning. Okay? In 7 weeks, we'll have a final exam, and you got to know your cards. So it's time to start integrating everything. Okay? Start integrating. So if I was trying to really learn this stuff, I'd use this slide and I would start listing examples so I can remember, okay? Which ones are gram-positive, which ones are gram-negative. Common infections, okay? Is that good? Okay, so far. Okay, so this is just a little reminder of the difference between gram-positive and gram-negative. Gram-positive has a huge peptidoglycan layer, okay? Gram-negative does not. But it has lots of proteins like porins that allow things into the cell, okay? And which one is easier to kill? Just saw the slide. Which one's easier to kill? Gram-positive. How come? Okay, we've got good targets, right? We've got that penicillin, okay? And we've got other things, as we'll see, that can help. I mean, because the microbes aren't just going to lay down and die. They've got enzymes that will help destroy penicillin. So, yeah, so this is what's coming. Okay, so whenever we look at a chemical or physical or chemical that we're going to use, something physical to control microbial growth, we have to look at concentration, okay? And then we have to look at what is the mode of action, okay? What kind of radiation are we using? Is it ionizing? Is it non-ionizing radiation? We have to look at polarity. Is something hydrophobic or hydrophilic, especially with chemicals? Because some chemicals, like surfactants, okay, they are able to have polar and non-polar parts of that chemical. So they will react with the cell membrane differently. They may react with the cytoplasm differently, okay? Then you have to use the optimal concentration, right? Okay, so we also have to look at things that are selectively toxic, all right? We want some things to, we want to kill the microbe with minimal effect on the host, okay? Because you're going to see, especially like when we talk about phenolics, those phenols, they're great. They kill everything. The aldehydes, they kill everything. But they're also toxic to human tissue, so we don't want to use them a lot. Okay. You want minimal side effects against the immune system or host tissues. You want to be user-friendly and effective. You don't want it to like have it go bad in 2 months. That's not economically good. Okay, we don't want it to cross the blood-brain barrier. That would be really bad. Okay, we have to look at dosage and can we do easy dilutions? Okay, we have to see if hopefully they have minimal resistance. The pathogens have not gotten any more resistance, and we have to look at how much it costs. Okay, my friends that their jobs are to develop new antibiotics, they said we can develop an antibiotic to anything, except it might cost you $40 million, and nobody's going to buy it. So yeah, you have to think about how much does it cost to control microbial growth. Okay, so far so good? Any questions you have so far? Okay, so microbial growth. So toxic to the pathogen, but not to the host. That's really it. And so we look at a number of things like plasma membranes. We look at proteins and enzymes, RNA, DNA, and ribosomes. We look at the cell wall. We look at whether it's a prokaryote versus a eukaryote. And we look at viruses. They are hardest to kill. Why?
They're rapid mutation.
They're not living. Yeah, they're not living, so they're hardest to kill. Okay. So we look for things that can cause membrane damage, okay? Just a second ago I mentioned surfactants. Surfactants have parts of the membrane that are polar, parts of that molecule are non-polar. And so what it's able to do is it can travel to the membrane through the phospholipid bilayer and disrupt it. And as soon as it gets in here, between here, because it's got non-polar and polar characteristics, now the cytoplasm can leak out. So we're looking at membrane damage for a lot of things, okay? All right, let's look at protein damage. Okay, we've talked about the tertiary structure. There was a question, depending on what version of the exam you had, about tertiary and quaternary structure of proteins. This is why, because here it comes again, okay? Yeah, so here's an enzyme, and what are the ways that we can stop it? We can have a heat or pH change that completely denatures it. Okay, we can have it that gives it a little different shape, or we can actually block the active site. And we'll see that with metals. We'll talk about how metal toxicity works, and that's what we can do. What happens is the enzymes will be destroyed by a lot of these toxic metals, and now the proteins don't work. So, okay, so pay attention to membrane and protein damage, okay? Okay, so you wipe your hands, let's check what you know here. You wipe your hands with an antimicrobial cleaner. What are you accomplishing? What are you accomplishing? Antisepsis, good. Okay, good. Does it help to have checks? See how you're doing? Okay, all right, good. All right, so let's talk about some practical concerns. All right, it's great to have things that kill microbes, but if it kills everything else, it's not good, so we worry about safety. We worry about cost. Is it practical and suitable? So in other words, does the application require it to be totally sterile? Does it not? Okay. Can the item that we're going to try and clean withstand heat, pressure, radiation, or chemicals? And oftentimes the answer is no, depending on what it is. So that's another thing that we're going to focus on as we go through these methods. Okay. Does it have an expiration date? Can the item be reused, or is it a one-time use? Okay. And will the agent penetrate to the necessary extent? Okay. Sometimes you've got a great cleaner, but if it's really hydrophobic and it doesn't penetrate in, it's really of no good. So, okay. Good? All right. So let's take a look at the spectrum of antimicrobial activity. So we've got the mycobacteria, gram-negative, gram-positive, chlamydias, and rickettsias. What is a disease that's caused by a rickettsia? What? What is it? What causes rickettsia? Okay, what disease? Okay, what diseases do ticks carry? Lyme disease, yeah, it's a rickettsia. Okay, again, what are we trying to do? Integrate all those cards that you've been working on now with actual real life things. So try and blend as much as you can. All right, I would also make sure I know some chlamydias, again, gram-positive, negative, and mycobacteria. Okay, mycobacteria and mycoplasma. So we talked about walking pneumonia, but what's the other one that somebody mentioned right off the top was TB, right? TB, okay? If we look at this, there's only one really good antimicrobial that we have for TB, isoniazid. Okay? Why? Because mycobacterium are weird. They don't have easy cell targets. They tend to hide into cells, and then they come back out and they hide from the immune system. So how long do you have to treat with isoniazid for TB? 4 to 6 months. Okay? Now, are your patients going to feel really good while they're on this treatment? Hell no. So what ends up happening? They stop taking it. And so now in Los Angeles and Riverside and San Bernardino County and Orange County and San Diego County, we have tons of drug-resistant TB. You can take this drug, but there's no guarantee you're going to ever fully get rid of the infection because it's resistant. Okay? All right. Well, let's see. Which antibiotic has the broadest spectrum? Tetracyclines. Yeah, tetracyclines are used a lot. Okay, for gram negatives, you've got a number of things that will cover it. some polymyxins, streptomycins. Gram-positives, you've got a little bit of coverage. And you can see why sometimes they give cephalosporins right away. If you're not, they know it's a bacterial infection and you don't have time for a culture and it's either gram-positive or gram-negative, at least you get coverage of both, okay? So, yeah. Yep, we're out of drugs. Okay, so, narrow or broad spectrum, what do you think is best? It depends, right? Okay, if you've got a bacterial infection and you're not sure, but your patient is, you know, going downhill, what would you use? Broad spectrum. If you use a broad spectrum on TB, is that going to work? No, it's not going to do a thing. All you're giving your patient is expensive poop. Okay? So, yeah. All right, so narrow spectrum antibiotics. These are antimicrobial that affect one type of cell, for example, penicillin or isoniazid. Broad spectrum, these are antimicrobials that affect many types of cells. And the best example we have from our chart is what? Tetracycline, yeah. Okay. Let's talk about microbial death a little bit, okay? We get interested, and we're having a conversation. Why, with our infectious disease folks, and we asked them, why do they give antibiotics for 14 days? You want to make sure it's completely gone, okay? Usually you're doing a gram-positive, and so as we'll learn next time, when you give you know, an antibiotic to a gram-positive, it like penicillin, it interferes with cell wall synthesis. So you got to wait for binary fission to happen before things start to die off. Okay. Why do they give things for 5 days? Yeah. Okay. It depends on the microbe and how fast it's growing. Sometimes 5 days is enough. Sometimes one shot is enough, right? So how do we figure all this out? Well, they start looking at microbial death. Okay. So time's over here, and microbe number is here, okay? Now, in real life, if we were to do this in lab, okay, make a nice little chart of this, we would start off and, okay, so here's time 0, and let's say at day 1, they give the medication, so right here. And it will start to go, and then, okay, it might go down, and then there might be some resistant ones that are there. That's great. Okay? What's wrong with this picture? Well, it's too curvy. It's way too curvy because you're looking at, you know, something that happens over a period of time. And you know, this might go out further, or the drop might be better, or you might not have any resistance, okay? But as long as you got curves in there, you can't make good mathematical predictions, okay? What do? That's why they use log of the number of viable cells. Because as minute you take a log of something curvy, what happens to it? It becomes a straight line when you take a log. Did you know that? Did you remember this we did this in 10th grade, I think. Yeah. Did you do that in 10th grade? No? Okay. That's all right. New math. It's okay. But this is why we don't like curves. Because when you've got a curve, the best is an approximation. You've got people's health at stake. I'm not going to make a guess on a curve. I want a straight line. So that's why they take logs. So as soon as you take the log of the numbers, then when you get on a logarithmic scale, oh, I can look at here and here and tell where half of my population is gone. Isn't that much easier than trying to approximate? Yeah, so I was looking at your book and looking at how they talk about microbial death, and I'm like, I bet nobody has ever really talked about why they do log. But that is important, okay? Have you got the difference between, you can't just go, you can go into lab and do this experiment, but is this good? Is this the data we can actually use? No, we got to take a log of it so we can get a nice straight line, okay? Is that cool? Okay, so when we talk about microbial death, we talk about permanent loss of reproductive capability under optimal growth conditions, okay? And usually things die at a constant rate, and you can plot what is called a death curve, which is log survivors or viable cells against time, which is what we just did. Okay, so let's take a look at these curves for a moment here, because they are kind of cool, because we can tell a lot from the microbe. Okay. Yeah. So what's interesting here? What does common sense tell you in terms of trying to sterilize something? Let's say I'm going to take all your plates that you're making for all your metabolic in your tubes, for your metabolic testing. What do you think will take longer to sterilize, a plate or a tube? A plate or a tube?
Two.
Okay, why do you say a tube? Yeah. Why do you say tube?
Because it's on a flat surface, it's caved in, and it makes it harder to evenly distribute.
Good, good. Okay, and a plate, what happens with a plate? It's right there on the surface, okay? So, do you think the autoclave times are going to be different? Do you want to autoclave everything together? No, because, well, the only way you could do it is if you set your autoclave time for the tubes, and the plates would automatically get done, right? You usually don't want to do that anyway. Okay, don't put them together. All right. What if you have a culture that's been growing 6 days versus a culture that's been growing for 4?
There are different points in the growth chart.
Okay, there are different points in their life. Which is going to take longer to clean?
The one at 6 days.
The one at 6 days. How come?
There may be endospores.
It's the number, and you might have endospores because of where they are in their life curve. So if I just say, oh, autoclave everything for 10 minutes, is that going to work? No, you have to think about what the differences are and what things might actually be growing. Okay, let's apply this to medical equipment. You've got intubation equipment, all right? You've got intubation stuff. A lot of stuff they just throw away, but if you're doing an endoscopy or pulmonary endoscopy, you go in, all right? Versus surgical equipment that does not go in the body, do you think you have to sterilize those differently?
Yes.
Which one would be longer?
The
The one that went in, yeah. And you'll say, oh, well, I don't ever have to worry about that. What? Maybe you will, okay? Talk to any nurse that worked during COVID. They were doing different things that they'd never done before. Why? Because we were out of people, okay? We were out of people. So there are a lot of things. And so some of my students have come back and said, yeah, I didn't have to worry about this. I didn't do this because, but because we were short of people, it happened. I hope that never really ever happens again. That was horrible. But you don't ever know, or you don't know what kind of hospital you're working at, and you don't know what's going to happen when they have power and stuff like that. Go out. Okay, so you kind of look here. This kind of makes sense. We've sort of talked through some examples about high versus low load. Okay, spores are harder to kill than the vegetative cells. So do you feel like you have a feeling for how you got to be thinking about the things on, okay, so which do you think would be dirtier? Your toilet handle or your phone? Oh, definitely your phone. Yeah, definitely your phone. Okay. Why? Number of contacts, right? Number of contacts, and people don't clean it. Okay. All right, good time. So don't lick your phone. Okay. Yeah. Okay, so we're going to start. We're going to go through 6 ways to physically control microbial growth here. Okay? Mechanical pressure, heat, cold, desiccation, osmotic pressure, lyophilization, filtration, and radiation. Okay? Okay, so let's start with mechanical pressure. Mechanical pressure, this is a scrubby scouring, okay? Or you can use sonication. How many of you have a sonic toothbrush? Yeah. How do they work? Ask our one of our dental hygienists isn't here. They work pretty well, okay? Why? Because not only do you have the scrubby, but you've got a high frequency vibration that helps to eliminate microbes, okay? So sometimes we clean equipment with what's called an ultrasonic bath. It's like a big metal thing, and you turn it on, and it's got sonic waves going through it, and you can clean all sorts of things, but yeah. Ooh. Okay, now let's talk about the heat, and think about a dishwasher, okay, to start with, but this is the use of hot water or steam. The mode of action is denaturing of proteins, DNA, and membranes. So this one checks all the boxes. Okay? We can use sanitizing hot water. We can use pasteurization, which is at 72 degrees from 15 to 20 seconds. Okay? We can use boiling, which is at 100 degrees C for 10 minutes to destroy the non-spore forming pathogens. Okay. We can do intermittent sterilization, where you use steam at 100 degrees. You're doing 30 to 60 minutes for 3 days. And then we've got autoclaving, okay, which uses 15 psi. What psi are we at normal, like at atmospheric pressure? What is our psi? Anybody know? I have to look it up, but it's not 15, I'll tell you what. Autoclaves, if they're not serviced right and that, they can actually have this happen at my job. Okay, my job, one of my first jobs for $5 and, well, I finally was making $5.25 an hour, is I would scrub test tubes all night long and clean them, and then have to autoclave them and autoclave material. And the autoclave that was on the first floor, they had a bunch of autoclaves, and they weren't, I was just a student, okay? But the powers that be weren't maintaining those autoclaves. That thing blew up, went through the wall, into the office. Luckily, it was the middle of the night when it happened. Somebody would have been killed. Okay? When you've got 15 PSI, that thing is a bomb. Okay? And, you know, those of you who have used them before, you know, how many have used one before? Okay, yeah. So you get that pressure down. If it doesn't come down at the right time, in the right space, and that thing will blow. Okay? So, yeah, people have been killed by autoclaves, yeah. And this was at a hospital. People came in the next morning and their offices were gone because the autoclave had blown up. Yeah?
Is it like a pressure cooker too? Is it pressure too?
Yeah, a pressure cooker, like Instapot or something. Yeah, you're increasing the pressure so you can kill more things, right? I mean, you're actually using it to cook. But it doesn't get up to 15 PSI. When we lock an autoclave down, it's a physical thing that you have to turn, and all the sensors have to be working correctly, and then you can go. Yeah. Yeah. Cool. Yeah.
I just looked it up for atmospheric pressure, and it says 14.7. Is that correct?
That seems a little high. Yeah. What is our normal PSI? it's going to vary. Yeah, it gives it a 14.7. No. Yeah, I'm gonna have to look that up. Because when you do a hyperbaric chamber, yeah, that's a high PSI too. Yeah, so I'll have to review some PSIs because I didn't look at them before I came in today. Okay, so how would you classify, whoops, whoa, okay, oh, there we go. Okay, so it takes, autoclaves go in cycles, so you might have, usually it takes about 2.5 to 3 hours, sometimes longer, to do it because you're doing 20-minute cycles. You do several 20-minute cycles, up and down in pressure, up and down in temperature. Okay, so how would you classify a dishwasher?
Sanitize.
What?
Sanitizing.
Yeah, it'd be a sanitizer. Does your dishwasher get everything? No. Especially not the ones they have on the market now. Okay. So, all right. In your book, you're going to read about thermal depth measurements. Okay. So, why is this important? Because you're going to look at thermal death time and thermal death point. Death time is the shortest length of time to get a certain amount of microbes under control to kill, and the thermal death point is how many is required. What is the lowest temperature required to kill the sample in 10 minutes? Okay. Again, definitions. You'll see these. And equipment usually that has to be clean. It will give you a TDT number or a TDP number, or both. Okay, let's talk about pasteurization. Okay, there's different kinds of pasteurization. If you had to explain pasteurization in one sentence, what would you do? What is pasteurization? Okay, what are you doing? You're using a high temperature to try and kill microbes, okay? All right. Now, where do you see pasteurization? Milk, juices, you get those little creamers, those are pasteurized, okay? When people want to drink non-pasteurized milk, it makes me very nervous because there's all sorts of things that can be growing in that, okay? So, high temperature, short time, okay? These are mostly drinks and things like that. Okay, UHT pasteurization, ultra high temperature. It's 135 degrees Celsius for 1 to 5 seconds to destroy non-spore forming pathogens. So these things are like the milks that you can see on the, that don't necessarily have to be refrigerated. So those little cream packs that they put out, that's UHT. Look at the label, it has to say UHT on it, okay? All right. Okay, that's cool, pasteurization. Intermittent sterilization. This is where you've got steam at 100 degrees Celsius, 30 to 60 minutes for anywhere from 3 to 5 days, okay? So what they do is they bring it up, the temperature up, let it cool down, do it again, do it again, do it again. So a lot of medical tools and dental tools are done with that. Okay, here we go. Here's an autoclave. That's a huge autoclave. That's a very big one. Okay. The ones that we have aren't quite so big, but what do? You increase the pressure and the temperature. Okay. And you can run it in several cycles. So it brings the temperature and pressure up and down, up and down. And by the time you get something out of there, it is what? How would we describe it? Sterilized. Good. Okay. Let's talk about dry heat. You use this in lab. You use Bunsen burners or hospital incinerators. Okay. Why? Because you're combusting the ash. Okay. Your loop does this. You flame your loop, right? What are you doing? You're burning everything that's off on it, okay? So this is 600 to 800 degrees Celsius for dry heat. Okay, so I put some, yeah, question.
We have the same one. So in the book, it says 1,870 degrees. SI said 1,100 degrees, and then you said 800 degrees.
Yeah, you're going to kill anything over 800. Yeah, you're going to kill anything over 800. Yeah. Unless it's got a metal in there, it won't burn any higher than that. You've got to have like a metal in there that can actually reach those temperatures, because yeah, you burn. Okay, so using heat for sterilization. I put some of the tables that are in the book, so you can go through here, and it gives, what I like about these is it gives, you know, different times, gives different pressures, gives during different temperatures that you might have, okay? And this is according to the latest edition of the book, okay? But it's there so you can help augment what you've got in front of you. Okay, let's talk about cold, okay? This is microbial growth inhibiting, so it inhibits the growth of microbes. Refrigeration is at 4, freezing is about minus 18 degrees Celsius, okay? We use it to preserve food, media, cultures. Oftentimes we'll use liquid nitrogen, which actually gets colder than that, but it doesn't kill things off. We have to put chemicals in that will help if we want to bring them back to life. Have you heard about that? Cryogenics, people are gonna freeze our bodies and come back to life. So they freeze them in these giant liquid nitrogen tanks that like would take up this room, you know, put the body in there and they're gonna bring it back. What's the problem with that? Bringing them back. I haven't seen anybody be brought back yet. Okay, we store all sorts of biological samples in live cell cultures we're using cryogenics, using cold temperatures. Okay, but they don't come back unless we preserve them and put lots of extra lipid and desiccation in there in the solution. Because if we don't do that, you know, the cell's mostly what? What is the cell mostly made of? Water. Water does what? Freezes, and it gets sharp when it freezes. And so it can cut through membranes. So you have to really protect cell membranes before you freeze cells, or else they're not going to come back. They're going to have all these fractured membranes. So I haven't seen anybody come back from cryogenics yet. Have you? Oh, I'm waiting. I think it'll be cool. But literally. So, yeah, so crazy. But cold temperatures, what do? They slow the growth. That's why you put your peanut butter in the fridge, so that fungus doesn't produce a lot of toxins. Okay. Desiccation. This is what we know as dehydration. Okay, what do? We remove water from cells, and what that happens when we remove water, that means that metabolic processes are inhibited. Okay, so when many cells can revive when water is reintroduced, but again, whenever you're trying to thaw something from cold or you're desiccating, are you going to get 100% of the cell's recovery? No, not from dehydration. Okay, so let's talk about osmotic pressure. Okay, what are the microbes that grow in high or low osmotic pressure? What are they? No, capno is CO2. Barophiles, yeah. So they can withstand different osmotic pressures, okay? So when we talk about salting and smoking, for salting, what are we doing? We're adding a bunch of salts to it, okay? And what ends up happening is you remove the water or water access to the cells, okay, by salting. So you have beef jerky, it's pretty well preserved. Why? Because you've salted it. You've put in some osmotic dysregulators in there, and all the water becomes unavailable for the cells. Okay? Same with smoking meat. I'm not talking about rolling one, I'm talking about smoking like meat. Okay? Yeah. So one of the things about smoking is, my family used to run a bunch of barbecue restaurants, so I know a lot about barbecue and how to smoke things. Again, not rolling, please. Okay, but how to smoke things and temperatures and things like that. Does anybody else here smoke anything? Yeah. Okay, wait a minute. Let me rephrase that. Yeah, meat. You smoke? Okay, what temperature do you smoke at?
Okay, that's my brother's job.
Oh, okay. He does the temperature? You just what?
I just put the seasoning on.
Oh, okay, cool. You do like try to? Cool. He does that part.
Yeah.
Okay. All right. We used to smoke our meats at 275. Okay? Because when you smoke, the longer and lower temperature, the more tender the meat comes out. And you have to get your seasoning right too, because what are you doing? You're adding a bunch of salts, which are desiccating. So yeah, you have to do it. So yeah, you don't cook barbecue like traditionally at a very high temperature. It's pretty low. Okay. All right. So you got to be careful what wood you use, right? What you just go? What do you smoke with? Do you smoke? What do you smoke with?
Like a smoker.
Yeah, but you have to put some fuel in there. What fuel do you use?
Like the
Oh, you use chips. Okay. Yeah. Okay. Okay. All right. Anybody else use anything different? Okay. I use wood, and I use apple and cherry wood because then it gives the meat like a sweeter flavor, like a fruity flavor. Just a little tinge of it. Okay. But my friends in Texas, I was out last week and saw their new smoker setup, and man, they're using a white oak, and it gave a really nice flavor to it. Okay? And how long do you have to smoke for? Again, we're talking about meat. Okay, how long do you smoke for? Yeah, about between 26 and 30 hours for depending on what the meat is. Yeah. Yeah, it takes a long time if you're going to do it right. Yeah, I mean, so we have to plan ahead. So what we're going to put in the smoker, because if we run out, we run out. We just can't go out and get it. Okay? And if you visit a barbecue place late at night, sometimes they don't have stuff. Why? Because it took a day and a half to smoke it before. So, yeah. Now, here's the other part. Smoking meat is not really good for you. Okay, why? Because it contains a lot of antimicrobial chemicals. So you think, well, we're told you got to have meat, above 160. Well, yes and no. Okay? If you smoke it long enough and correctly, okay, between the salts that you put on there, the temperature you did it, and the time, and then the crap that's made to make it taste so good, the carbon on there to make it taste so good, that has a lot of antimicrobial properties. If you go in and try and smoke stuff and you don't get the right time or the right temperature and you don't put it in long enough to make those, you can get really sick from the stuff. Okay? Yeah, I mean, yeah, crazy, huh?
Is it true that rare TV qualified that they has a lot of carcinogens?
It does. It does. It has what are called PAHs, polyaromatic hydrocarbons. Not that I expect you to remember that, but yeah. That's actually a risk factor for all sorts of cancers, is smoked meat. Yeah. So is smoking. Okay. All right. Oh my goodness. Yeah. got a story about it. Okay, so one day, okay, so I came into work late, and because I had worked and closed the night before, so I got done at 2 or 3 in the morning. So I came in, and my brother-in-law, he usually runs the smokers and stuff, and so I'm looking at the wood, and I hear like, Heather, get over here. Okay, it's like, can I use this wood? And it was like this nice piece of wood. If this was wood, it was about this big, and it had this giant shelf fungus on it. And what would you say? Yeah, I said, no, dipshit. What do you think? You think you can do this? What are you talking about? I said, that's a fungus. By the time you see the reproductive parts of the fungus, the mycelia are all through there. And you've got spores being made. I said, you got to get rid of this whole wood pile. Because at 160 degrees, are you going to get rid of endospores? No. I said, you want a bunch of high sick people? A bunch of lawsuits? And he's like, oh, I'm glad you went to college. Yes. The joys of math. Anyway, okay, so let's talk about freeze drying things. Have you seen things that are freeze dried? Okay, what do we do when we freeze dry something? Okay, you get cells, and they're usually you can usually get them from a frozen state, okay? And then you put lots of preservatives in there, okay? And you can store it, use it for storage, okay? So, instant coffee, that's a big one, okay? That's a food that we liofilize. And so, when we do this, because there's no water in there, it's been desiccated, you don't get a lot of microbial growth. You still usually put some kind of preservative in there for commercial, but take a look at anything in your house that's freeze dried and see if they added any other chemicals to help keep its shelf life up, okay? All right, now, what if water gets into this? Yeah, all bets are off. Yeah, all bets are off. Because as soon as there's water there, what are you going to have? Growth. You're going to have things growing, right? Okay. So if you can look up, we have cells that we order from ATCC, which is a repository of tissues and cells and things like that have been freeze-dried that we can bring back. Okay, let's talk about filtration. This is a physical method to remove microbes, okay? And the way that you do that is you pass gas or liquid through a filter, okay? And you can kind of see this is a nice little filter thing on here. And you've seen this, and sometimes when they give injections, right? They stick a filter on, okay, before they give it. There's some medications that tend not to dissolve very well. And what do? They put a little 0.5 micron or 0.1 micron filter on the injection, and then they give it, okay? So what are they doing? They're actually using a physical filtration method. Oftentimes, if it's a medication, they're looking to get rid of any crystals or things, molecules that haven't dissolved properly before they give that, because they don't want that, coursing through veins and stuff. But yeah, so that's what they do. Okay, why use this? This is really good for heat-sensitive liquids. Okay, if you've got medication that's an antibody, if you've got a liquid that if you heat that up, it's going to denature everything. So don't want to do that. Okay, let's test your not have a knowledge extravaganza here. What if the following accomplishes biocidal effects? All that apply. Biocidal. Okay, you got your answer? What'd you come up with?
A, B, and C.
A, B, and C. Good. All right. How many of you got it right? Good. Okay. All right. Let's see how we're doing. Oh, good. All right, let's talk about radiation for a little bit. Okay? This is the visible spectrum. So it goes from about 400 to 700, or it starts out over here, 400 to 750 nanometers. Okay? Anything over here, high energy. Everything over here, low energy. So radio, low energy. What about your TV clicker? Where does it belong on here? What's your TV clicker? Infrared. What's signaling on your phone? Most of it is infrared. Okay. All right. Pretty low frequency. Okay. Gamma and X-ray, these are high frequency. What do I mean by frequency? Okay. When you look at this versus this, which wave has more energy? The one on the left, right? Okay. This is like the color red. It's really relaxed. Okay. Longboard surfing here. Okay. This is high energy shortboard. This is like violet or X-rays. Okay. This is more like red and infrared. Okay. Because you want to get an idea about energies and how these work, because these waves can do a lot of biological damage. Okay, but some of it can repair. Have people been reading about those infrared healing lamps that'll heal your skin? Yeah. Do they work? I don't know. It depends on the frequency. Yeah, it really depends on the frequency. They've used infrared for healing soft tissue in physical therapy for a long time. But if we get over here, X-rays and gamma rays. Okay, it is really critical that you as a healthcare worker know the difference between ionizing and non-ionizing radiation, and what radiation does and what radiation can do to help you and to hurt you. I will give you, in 1987, there was a dirty bomb that went off in a town in Brazil. Okay, what is a dirty bomb? Is it a nuclear weapon? No. It's somebody stole the cesium source from a hospital, put it into an explosive thing, and blew it up. Okay? All right. That happens all the time. One of my tasks in 2005 and 2006 was finding, stolen irradiation sources out of Ukraine. Okay? Yeah. I mean, this is a thing. When something happens, and what happened in Brazil in 1987, this dirty bomb went off. And the medical staff left the hospital because they didn't understand radiation. That means the physicians, the nurses, anything. And when you have a dirty bomb that goes off, most of your patients are not going to be radioactive. They're going to have blast injuries. Okay? Can you imagine the medical staff over across the street just leaving? They couldn't treat anybody. And the problem was they didn't understand what radiation is. Okay? You need to understand this. Okay? There are radiological events that happen all the time. The most major one recently was probably Fukushima. I think it was probably the last global one of impact. Chernobyl was before that. But if you don't understand that, is a patient radioactive or are they not? Okay? That's not good. That's not good. Okay? Because you could put them at risk, you could put other people at risk, you cannot be treating the patient the right way. So it's important to understand the differences between radiation. Okay? Is that cool? Okay. So we're going to talk about the two kinds. All right? Ionizing radiation, it blasts cells. It blasts DNA apart. These are things like X-rays, gamma rays. Okay? Now let me ask you a question. If you get exposed to an X-ray you get an x-ray of your arm, is your arm radioactive? Absolutely not. But there's a lot of people that think they are. Okay? When you have something that's high energy, it's going to go right through the tissues. The only way that something is high energy like that is if it's like dust that gets on you. It's radioactive. Okay? Then what do? Scrub with soap and water and a good brush. That'll decon most of it. Okay? Yeah. It's not anything to be afraid of. You just have to think about, what is actually happening. UV light. We already talked about this. This was on your exam. What is this? That's a thymine dimer. We already talked about how you can get photoreactivation and all this stuff to do it. Okay, so when you talk about non-ionizing radiation, it's little penetrating power. Okay? It sterilizes air, water, and surfaces. Okay? Think about when COVID hit. Suddenly, every airplane had a robot with UV light that was going up and down overnight, the aisle, not serving any drinks, but just glowing. So what? It could clean the airplane. Okay? Does UV light damage viruses? Yeah, it does. Okay? That's why we use UV light. If you're working at a hospital, find out how they're cleaning their air. Oftentimes on the fresh air intake, as part of their cleaning through HEPA filtering, okay, they will use UV light to get anything else that might have come through. Okay? So, UV light is about 260 nanometers and it creates thymine dimers, and we've talked about how that works. Okay? UV radiation water treatment in the new water plants that are being built around the country, not so much in California, unfortunately, but they're using UV light to help clean the water. Okay? It's really an interesting technology. The most expensive thing on here are these bulbs that make 260 nanometers. That's what's really expensive. Okay? So, ionizing radiation, high or low power? Very high power, high penetrating power, breaks DNA strands, gamma rays, X-ray, cathode rays. Okay? We can use this to sterilize medical supplies. Okay? When a person goes in for radiation therapy, are they radioactive after? No. The waves go right on through, treat the tissue, off they go. Okay? Now, somebody has a PET CT that has radiation in it. Are they radioactive after being injected with it? Yes. Why? Because it's in their body. They're going to be hot, and not in the good way, right? Okay, yeah, radioactive hot. Okay. Now, I wish that we used radiation to sterilize everything. If we used ionizing radiation in our meat supply, our meat would have a shelf life of 90 days. Okay? Without refrigeration. Okay? Why? Because you killed all the microbes. But then you've got people that are like, oh, the food's going to be radioactive. Is that true? No. Oh, it's going to degrade the proteins. Does it do that? No. What does it do? It targets membranes and mostly DNA. Okay? All right? So, here's raspberries that were treated with radiation versus raspberries that were not. Which one has a better shelf life? The radiation one, yeah. Okay. All right. I'm going to stop there because we're going to talk about bacon, and we'll do that. Okay. Hey, it's bacon time.